So conservation laws are going to have kind of their own procedure, which is going to be, I kept advertising in the first part of the course how if you grasp that F equals MA procedure, that's how you solve like the whole first portion of the course. This right here is going to be how you solve almost all the problems in the last portion of the course, conservation laws. So it's going to actually be pretty similar to how we solve kinematic equation problems, if you remember that. Let me go through it. So step one is going to be to identify the system whose momentum is conserved, which is one of those things that sounds very simple and straightforward, but is an important step because there are a lot of cases where people start to get confused about exactly what am I supposed to include here. So if you want conservation of momentum to apply, let me write this down. For conservation of momentum to apply, you must include both halves of the Newton's third law pair. You must include the action and the reaction, as people would say. You must include both of the objects that are interacting. Otherwise, because it is, of course, possible to change the momentum of an object if you're not looking at the other object. So you have to be watching both objects whose momentum is changing. Okay. Number two is going to be to identify the initial and final states. Just like in kinematic equation problems, identify what is a clear, very specific picture of what am I doing as, because this is delta P, remember, that we're considering. So what is the initial that I'm subtracting off, and what is the final that I'm adding on? So what is the initial state? What is the final state? The third step in my procedure is to sketch the initial state and the final state. Sketch the initial and final states. Fourth step, momentum is a vector, so make sure you know which way is positive and negative directions for your momentum vectors. Again, a small step, but something that can easily go wrong for people. Now, this is where the real action starts in terms of like calculation. Next, you want to obtain all the momentum components with their signs. So you're going to have some momentum vectors because of the velocities involved in the problem. You're going to take each object, take the mass times the velocity. If necessary, if it's a 2D problem, break it into components. If it's a 1D problem, just identify what's positive and what's negative in this problem. Because like with most of the other problems in the course, we're going to do this all in component form. Then 6, you're going to sum the total momentum of all objects in the initial picture. You're going to sum the total momentum of all objects in the final picture. So you want the total momentum. So if it's a 2D problem, you'll sum all the X components and then separately sum all the Y components. If it's a 1D problem, you just sum it up with the negative signs included. And then lastly, where you apply the conservation law, you now set the initial momentum equal to the final momentum, because that is the conservation law. Or if you're doing an impulse momentum problem, you might set the delta P equal to the impulse, if it's a one of those style of problems. So I said this is like the kinematic equation style problems because you'll notice a kind of overarching similarity here. The main concept is identifying the initial and final states, writing down all the important information about the initial state, writing down all the important information about the final state, and then finally applying the physics to construct an equation. That kind of flow is the same as kinematic equation style problems. So these problems, if you just follow the procedure, they're very easy, but a lot of students get tripped up on them. So be careful to kind of try to absorb this. And we'll do definitely some examples in the next video or videos.